So we now have all the language we need to state one of the most famous theorems in all of mathematics, and that's the fundamental theorem of algebra. So here's what the fundamental theorem of algebra says. Every monic polynomial uniquely factors as follows. The polynomial is equal to a product of a bunch of terms, where the first term is t minus r1 raised to the m1. The next term is t minus r2 raised to the m2. And then we keep going until we get to t minus r sub k raised to the mk. So every polynomial factors like this, where r1 up to rk are the distinct roots of the polynomial, and the powers that occur in this factorization all add up to the degree of the polynomial. The powers that occur in this factorization are called the multiplicities of the roots. So m sub j here is the multiplicity of r sub j as a root of the polynomial. So if you know all of the roots of the polynomial and you know their multiplicities, you know that you can factor the polynomial like this. So let's look at an example here. So here we are given a factorization. This polynomial, f of t, is factored as t plus 2 minus 3i cubed multiplied by t plus 2 plus 3i cubed plus t plus 7 to the fourth. What can we infer from this factorization? Well, the first thing we know is if we add the multiplicities together, 3 plus 3 plus 4, we get here the number 10. So this is telling us that the degree of our polynomial is equal to 10. The next thing we can do is we can figure out the roots from this equation. Remember, in the fundamental theorem of algebra, the factors are t minus the root. So here, t plus 2 minus 3i is the same thing as t minus the quantity negative 2 plus 3i. So the first root of this polynomial is negative 2 plus 3i. Then the second root would be negative 2 minus 3i here. And the last root would be negative 7. So this factorization immediately tells us the degree of this polynomial and that this polynomial has three roots given by negative 2 plus 3i, negative 2 minus 3i, and negative 7. And that's exactly what we've inferred here. The degree is 10, and the roots have multiplicities m1 equals m2 equals 3, and m3 equals 4. The task of factoring polynomials, so the task of starting with a polynomial and then factoring it, is a very old problem in mathematics. And this is a very well understood problem for certain degrees. One of the most famous formulas in all of mathematics is the quadratic formula, which is really just a procedure for telling us how to factor any quadratic. And this is the theorem that tells us that every polynomial a times t squared plus b times t plus c factors as the number a, so the leading coefficient, multiplied by the quantity t minus negative b minus the square root of b squared minus 4ac, all divided by 2a. Then the second factor is t minus negative b plus square root of b squared minus 4ac divided by 2a. So the quadratic formula gives us the roots of any quadratic, and the fundamental theorem of algebra tells us how to take those roots and write down a factorization of any quadratic. So here we have an example. Here we're studying the polynomial negative 2t squared plus 8t minus 10. So I've managed to factor this polynomial as negative 2, that's my a here, multiplied by t minus 2 minus I, multiplied by t minus quantity 2 plus I. Now, where did this factorization come from? Well, if we apply the quadratic formula, we get two roots. The first one should be negative b, so negative 8, minus the square root of b squared, so 8 squared, minus 4 times a, which is negative 2, times c, which is negative 10, all divided by 2a, so 2 times negative 2. And when we simplify this root, we end up with 2 minus I. What about the second factor here? Well, that's obtained by applying the quadratic formula to get the second root. Instead of negative 8 minus this square root, we get negative 8 plus this square root to get our second root, 2 plus I. So the quadratic formula allows us to factor any quadratic polynomial, so any polynomial of degree 2. So the one thing to point out here is that this is a real polynomial, so the polynomials have this polynomial has real coefficients, yet its roots are complex numbers that aren't real. However, they are related by conjugation. 2 minus I is the conjugate of 2 plus I. So that's one thing to keep in mind. Now, once one learns that there is a quadratic formula, it's quite natural to ask whether or not there are formulas for higher degree polynomials. And it turns out that this is very well understood. So there's a theorem that says for a degree 3 polynomial, there is a formula. So there is a cubic formula. And it also turns out that there is a quartic formula. So for any degree 4 polynomial, you can write down an explicit formula for the roots of that polynomial. However, there's a very famous theorem, which was proved by this mathematician named Abel in 1824, and his theorem is absolutely remarkable. It says that there is no quintic formula. So this theorem not only says that people have not found a formula for the roots of a polynomial of degree 5, Abel proved that you will never find a formula. The theory is polynomials of this degree are simply too complicated to find a formula for. And I always thought this was an amazing theorem. So this theorem is amazing, but it does have a downside, which says, well, if your polynomial has a degree bigger than 4, the project of finding the roots of that polynomial is quite difficult. So what people do in practice is they use approximation algorithms to find roots.